Welcome to the Electrical Grid Testing and Commissioning Training, Module 2, where we will focus on current transformers. This module is designed to give you a comprehensive understanding of testing and commissioning processes essential for electrical grids. Let's dive in and explore the critical role of current transformers in maintaining grid reliability. Here we have the reference framework for testing and commissioning the electrical grid. This slide outlines key organizations and standards that serve as the backbone for our commissioning manual and test scripts. Some of the most important references include IEC, the International Electrotechnical Commission, and IEEE, which stands for the Institute of Electrical and Electronics Engineers. These bodies develop widely recognized standards that ensure reliability and safety. Additionally, ASTM, the American Society for Testing and Materials, provides guidelines on material testing, while NEMA and ANSI contribute with manufacturer and national standards respectively. We also consider CIGR, which focuses on large electric systems, as well as ICA and KEMA, which handle cable engineering and electrical verification. It's crucial to apply the most stringent requirement among project specs, manufacturer instructions, and standards when they differ. This approach guarantees the highest quality and compliance. Also, always record the reference used on the test sheet so future reviewers can clearly understand the accepted results. Here we have the schematic for insulation testing of current transformers, which is crucial during the testing and commissioning of the electrical grid. This diagram serves as a reference for performing insulation tests between the primary winding and ground, the primary winding and secondary winding, as well as the secondary winding and ground. Ensuring proper insulation in these areas is vital for the reliable and safe operation of the transformer, preventing faults and potential failures in the system. This process is detailed in our commissioning manual number 2-1. On this slide, we focus on the current transformer insulation testing process, a critical step before functional testing in electrical grid commissioning. First, we verify the CT details like tag, ratio, and polarity and ensure all circuits are safely isolated. Using a 5 kV or 500 V DC insulation resistance tester, we methodically test primary to ground, primary to secondary, and secondary to ground insulation by applying specific DC voltages and monitoring readings for stability. It's essential to discharge the circuit after each test and never leave it in an unsafe state. We carefully document all test parameters, including voltage, resistance, and ambient conditions, and restore wiring to the approved as left condition. Acceptance criteria demand stable insulation values with no signs of breakdown or abnormal discharge. Finally, a witness confirms that secondary safety and terminal restoration meet standards before the CT circuit is closed. This ensures the integrity and safety of the transformer before moving forward. Here we have the schematic for the current transformer turns ratio test, which is essential for ensuring accurate performance of the transformer. This test verifies the correct ratio between the primary and secondary windings, which affects measurement and protection functions in the electrical grid. Using the CPC 100 or similar test equipment, we can accurately assess this ratio to detect any discrepancies. This step is a critical part of the testing and commissioning process, helping to maintain system reliability and safety. On this slide, we're covering the current transformer turns ratio test, which is a crucial step in the testing and commissioning of the electrical grid. The main goal here is the verification of the actual turns ratio, proper tap selection, current injection, and ensuring the accuracy class requirements are met. We reference WING 6460-002-023 and use information from the CT nameplate, as well as protection and metering core schedules, alongside an approved ratio test form. The instrument used is typically an Omicron CPC 100 or an equivalent CT ratio test set, which might include a current booster when needed, plus grounded power supply and printing or export capabilities. The test procedure involves 8 clear steps: setting up the instrument on a stable base with proper power and grounding, identifying all relevant terminals and components, confirming the CT is de-energized and isolated, connecting the instrument properly, powering it up and selecting the suitable test mode, entering the necessary data like nameplate ratio and injection current, running the test across all taps, saving results and recording key parameters such as ratio, phase angle, and deviation, and finally, restoring the burden connections, and completing a witness review of results. Acceptance criteria dictate that measured ratio and phase error must meet the CT nameplate, accuracy class, and approved protection or metering specs. The result package should include test cards, a tap and core result table, a nameplate photo, instrument certificates, burden isolation records, and a witness signature. Lastly, a critical hold point is that the witness must confirm all cores and taps have been tested and that the burden wiring has been correctly restored before proceeding. This ensures the reliability and accuracy of the current transformer's performance. Here we have the schematic for the current transformer excitation and its kneepoint, which is essential during testing and commissioning of the electrical grid. This diagram serves as a reference to verify the CT's excitation curve and ensure the kneepoint is accurately identified. Understanding this helps us confirm the CT's performance and reliability in real-world operation. This information is detailed in Commissioning Manual number 2 to 3 for anyone needing further guidance. On this slide, we focus on the current transformer excitation, or kneepoint test, which is essential for verifying the excitation characteristic, saturation behavior, and protection core suitability of the CT. The test follows a detailed script referencing WING 6460-002-023 and requires specific equipment like the Omicron CPC 100 or an equivalent excitation test set with grounded supply and measurement capabilities. We start by confirming the CT core, tap, class, and protection function that require verification. Next, it's important to isolate the CT secondary circuit and disconnect burden wiring as per the approved test plan. Then we set up the test instrument with proper protective earth connections to the selected secondary core or tap. Once powered on, the instrument is set to the CT excitation test mode, where necessary voltage limits and core or tap identification are entered before running the test. The excitation curve is saved and repeated for all required cores or taps. After testing, we carefully review the excitation curve, focusing on the kneepoint and current behavior, comparing them to design expectations and previous baselines. If there are any unexpected low kneepoints or abnormal curves, further investigation is necessary. Finally, we restore all secondary wiring and shorting links, attaching the curve printout to the test sheet. The acceptance criteria demand that the excitation curve and kneepoint align with the CT class, protection application, and approved design criteria for a successful test. Our evidence package includes the excitation curve printout, core/tap table, instrument certificates, records of burden isolation and restoration, and witness sign-off. A critical hold point requires a protection witness to verify correct core and tap selection and final secondary restoration before releasing the circuit. This ensures the test is thorough and the system is safe to operate. Here we have the schematic for testing the winding resistance of a current transformer. This diagram is crucial because it guides us through the proper way to measure the winding resistance, ensuring the transformer is functioning correctly before commissioning. It also includes important safety cautions related to the secondary side to protect personnel and equipment during testing. Following this schematic step-by-step helps prevent any damage and guarantees accuracy in our resistance measurements. This document is part of our commissioning manual, specifically Manual number 2 to 4. Which provides detailed procedures for safe and effective electrical grid commissioning. Let's go through the current transformer winding resistance test procedure step by step. First, it's crucial to verify the CT tag, selected core or tap, and ensure the burden is isolated along with proper terminal identification before connecting any instruments. Next, set up the testing equipment, like the Omicron CPC 100 or an equivalent device, on a stable base with protective earth and the correct auxiliary supply. Then, carefully connect the current and voltage leads following the winding resistance schematic. Once connected, power on the instrument and select the appropriate test mode for winding resistance. Enter the core or tap identification and perform the resistance measurement, waiting until the value stabilizes. Save the test data and repeat this process for all necessary cores and taps. Before disconnecting, confirm all warning indicators are off and that complete discharge has taken place to ensure safety. Finally, restore all burden wiring, secondary shorting, and terminal covers before closing the test sheet. Remember, the acceptance criteria require the winding resistance to be stable, reasonable for the CT design, and consistent across comparable cores or taps. Any abnormal deviation or open circuit is unacceptable. Also, never open the measuring circuit while current is flowing. A witness must confirm that testing currents are off and circuits are safely restored before disconnection. The result package should include the winding resistance printout, core/tap table, terminal photos, instrument certificate, restoration records, and witness signature to maintain thorough documentation. Here we have the schematic for the current transformer voltage withstand test, which is crucial for ensuring the transformer's ability to handle high voltages safely. This diagram serves as a reference for both the voltage withstand testing process and the associated high voltage safety controls. Following this schematic precisely is essential during the testing and commissioning of the electrical grid to maintain system reliability and operator safety. This information is detailed further in Commissioning Manual number 2 to 5 for your guidance. On this slide, we focus on the current transformer voltage withstand test, which is critical for ensuring the dielectric integrity of the selected CT secondary insulation boundary. The reference for this procedure is WI-NG 6460-002-023, which outlines the approved voltage levels, duration, connection diagrams, and required safety permits. We use instruments like the Omicron CPC 100 or equivalent, along with high-voltage leads, barriers, discharge tools, and calibrated record output to perform the test. The step-by-step script starts with reviewing all approved parameters and confirming the CT is de-energized with secondary connections isolated. Then we set up the grounded test instrument, install barriers and warnings, and connect test leads according to the schematic. It's important to power on the instrument, select the correct test card, and enter the approved settings carefully. During the test, we monitor for any breakdown, trips, abnormal noises, or leakage that might indicate a fault. After completing the test, saving the records and fully discharging the equipment is essential. We repeat the test for all required core or tap combinations if specified, then restore all secondary wiring, shorting links, and covers before sign-off. The acceptance criteria require no insulation breakdown, flashover, or abnormal leakage within the test duration, following project and manufacturer limits. For documentation, we compile the voltage withstand test record, settings screenshots, instrument certificates, safety photos, restoration checklist, and witness sign-off. A crucial hold point is that the high voltage used is life hazardous, so a witness must confirm the exclusion zone, test completion, discharge, and restoration before anyone is allowed access. This ensures the utmost safety throughout the process. Here we have a schematic for checking the polarity of a current transformer, which is crucial during testing and commissioning of an electrical grid. Using devices like the CPC 100 and the CPOL polarity checker, we can accurately verify the correct polarity to ensure reliable operation. This process is detailed in Commissioning Manual number 2 to 6, providing a clear reference to follow for proper CT polarity verification. Getting the polarity right is essential to avoid measurement errors and ensure system safety. On this slide, we're focusing on the current transformer polarity check, a critical step in testing and commissioning electrical grids. The main goal here is to verify the CT primary and secondary polarity, core direction, and that relay or meter connections are correct. We follow the procedure outlined in WING 6460-002-023, using the CT nameplate, polarity marks, secondary terminal schedule, and the approved wiring diagrams as references. We use specialized instruments like the Omicron CPC 100 with a CPOL polarity checker, along with test leads, terminal labels, and calibrated record sheets for accurate testing. The step-by-step script begins by confirming the orientation of primary and secondary terminals, isolating the CT circuit, and setting up the grounded test instrument following the schematic. We inject a special polarity check signal and verify the indication at the secondary terminal. If the CPOL shows green, that's correct polarity, but a red indication means inverted or distorted polarity, which must be corrected. This check is repeated for all cores, taps, and phases. If wrong polarity is detected, always turn off the test set before making any disconnections or corrections. After adjustments, restore all terminals and wiring, then close the test report. The acceptance criteria require polarity to match all markings and diagrams. Any inverted polarity must be fixed and retested prior to acceptance. Finally, a witness verifies the final CT polarity and wiring restoration before energizing any protection or metering functions, ensuring safety and accuracy.